So let's continue on with this problem we were trying to solve for projectile motion. Before I move on to range and maximum height, I want to emphasize again the time in the air. I took the approach, and you got to understand this conceptually. So if the object goes up and then down, I took the approach of finding the time for this part right there, for the half the flight. And what I know at the peak, and this is important, is that the Vy is 0. Vx is not 0. Let me emphasize it, but that doesn't matter for time in the air. So I said my final speed was 0 here. My initial speed was v sine theta, because that's the initial y component. And then I could use the first equation over here, v equals v naught plus at. For a, I put in negative g. And then to get the correct answer, I had to multiply by 2. So this is a time to go from here to here, or the half time, and then I have the time it takes to come back down. That's my other half time. So then I get the full time. I could have done this a different way. I could have done it, and I'm not going to do it algebraically, but I'll explain to you conceptually I could have done that. So if I've got that flight, I could have said my initial speed, again, is v sine theta. That's not different. And then I could have said my final speed at the bottom is v is equal to negative v naught sine theta because of that symmetry. So if I go to I'll get the full time. If I subtract these two, I don't get 0. I get negative 2v sine theta divided by g right there, and I get the same equation. Okay, so convince yourself of that, because it's really important you be able to do that. Now, for the range, it's a little bit easier. Range is a horizontal position. So go back to my VTAX, this is what I'm looking for. I know the acceleration is 0. I know the initial horizontal speed. I just need the time. Well, we just found the time. The time was based on this equation. So why don't I put in a time here? I'll actually do the calculation. So I've written the equation again down here. I'm not going to substitute the numbers on the screen, the smartboard, but if I put the numbers in my calculator, I get 3.86 seconds. Okay, so it took half of that to get to the peak, and then double it to get the full. That's where that 2 comes from again. Now to find the range. So I'm going to do the range over here in that part, which is more space for me to work it out. So we've got a time in the air. So range is a distance. So I know distance, a time, I know initial speed and acceleration. So the general equation I'm going to use is simply my change in x is v naught t plus 1/2 at squared. So there's the general equation. It's right up here. You can see that for yourself on a paper. So let me substitute in what I know. So I'm looking for delta x. What is v naught in the x direction? Don't put in a launch speed. That's v naught cos theta t plus, or actually, let me be careful there. Well, 1/2 at squared. Well, what do you know about the horizontal acceleration? That's 0. Okay, so it just reduces to this equation, which is pretty straightforward. So if I go down here for range, I'm going to write delta x is v naught cos theta. There's my vx times t. So if I do 33, there's my initial speed times the cosine of 35, and I multiply it by 3.86 seconds, of course I get the range. So we can do that. And that's about 104 meters. The number isn't really so important, so you understand how to get that. Now the maximum height. So maximum height is a y. That's right here. What we're looking for, what do we know? Well, here's the important thing. We know, we have the time, right? That's 3.86, but let's say we didn't know the time. We know the initial speed, we know the acceleration, and we know the final speed at the top is 0. So we can use that information again and use the equation. So I'm going to do it right up here for maximum height. Is I'm going to say, okay, I know initial speed, final speed, acceleration, and looking for distance. That's just your v squared equals v naught squared plus 2a delta x. So in this particular problem, before I put in numbers, final velocity squared is 0 equals v naught is v launch sine theta, okay, quantity squared minus 2g delta y. So if I want to solve that algebraically, delta y is nothing more. The negatives are going to cancel out here. So v naught sine, theta quantity squared all over g. which is just a variation of v squared over acceleration, which we have seen before. So if I plug in the numbers here, I'm going to do 33 times the sine of 35, square that, and then divide by g, 9.8, and I get a maximum height. I'm going to call that y max of 36.6 meters. Okay, so look over those carefully because the algebra is a little bit more involved, but it's the same physics. Now, here's another problem you want to be able to do without having to do calculations, is how will things change if I simply change the angle? The launch speed is still this. Okay, I'm just firing it at a bigger angle. So 35 is like this, 55 is more vertical. So what will be true of the vertical speed? It's going to be greater, or it's going to increase. We're simply firing it more upward than outward, so it's going to be faster, and conversely, the horizontal speed is going to decrease. Okay, how about the time in the air? Well, we saw on the front page that time in the air is proportional to the angle. It's the sine of the angle, and the bigger the angle, the bigger the sine of that, so that's going to increase. That's pretty straightforward. The height should make sense, is going to increase as well because you're firing it at a bigger angle. The one that's the most difficult is the range. And so conceptually what I said to do is look at how close it is to 45 degrees, because that's the maximum, and everything goes from there. So 55 is 10 degrees away, 35 is 10 degrees away, so the range will be the same. And again, the mathematical expression for that, why that is that the range is proportional to sine of 2 theta. So if I put in 2 times 35 and take the sine of that, I'll get the same thing as if I do sine of 2 times 55. Where this comes from, I will derive later on. Okay, so I'm going to go back to one thing I forgot to do on the front page. And you might be wondering, is he going to talk about that? And that's right here. It says, why is the range of 20 the same as 70? In other words, why are complementary angles give us the same range? Well, I'm going to give you I'm not going to give you a rigorous answer. I'm going to give you a fairly simple answer. So let me draw those vectors again. This is like this. This is like this. They're both launch at the same speed. In essence, range is simply equal to Vx times time in the air. Okay? Simply how fast you're moving forward multiplied by how much time you're moving forward. We just saw in the previous problem that time in the air depends on the sine of the angle. Okay? So in other words, when you fire something at 20, you have a big Vx compared to 70. 70 has a little Vx because 70 is more vertical, it's less horizontal. However, since 70 is more vertical, it's going to be in the air a long time, whereas 20 is going to be in the air for a much shorter period of time. So these two kind of balance out. It's not a proof why complementary angles give you that, but it's giving you an idea that there's a balance when you fire something at an angle between how fast it's moving forward and how much time it's in the air. And 45 gives you the optimal of that. Okay, so good luck with the practice problems. I know you're going to feel like you're going to struggle, but really, if you take your time and break down to VTAX and understand, at the peak, it's not moving vertically, but it is moving horizontally, I think you'll have success.